everyone, this is Miss Chelsea, and today we'll be learning about heating and cooling curves. Our question of the day is, which heat equation would you use if you were considering a temperature change, melting or freezing, and boiling or condensation? Our current standard is SC5B, which is to construct an explanation using a heating curve as evidence of the effects of energy and intermolecular forces on phase changes. Now, keep in mind that heating and cooling curves track kinetic and potential energy changes at a constant pressure. Now, the average kinetic energy is a measure of how quickly particles are moving. This is directly related to temperature. Particles will move fast and cold particles will move slow. Therefore, since temperature is the average speed of all the particles in a sample, as the speed of the particles go up, the thermometer reading will also go up. Example here, we actually have different particles. We have some that are slow and some that are faster, but the thermometer itself reads the average speed, so the middle speed. Now, potential energy is a measure of stored energy in a substance or system. The further apart particles are, the more potential energy you have. Gases have the largest amount of potential energy because the particles are the furthest apart. Meanwhile, solids have the lowest potential energy because they are the closest together. And liquids are intermediate because they're pretty close together, but they can flow around a bit. They have a little space to move. We've reviewed that. Let's look at heating and cooling curves. On the sloped lines, kinetic energy is changing, so the temperature is changing whenever we have a slope. For example, if we look at this heating curve, this non-zero slope means that temperature is changing. This one means that temperature is changing, and this one means that temperature is changing. During a phase change, the temperature will not change. We will have a constant slope. Now, these occur on the plateau lines, where potential energy, or the distance between particles, is changing instead. So on these two lines, we're actually keeping the temperature constant, but because we're using our energy to help the particles spread apart and change phases, we still have to add energy during that time. Now, once again, on a heating curve, sloped lines are where kinetic energy increases, and flat lines are the endothermic phase changes. So, the sloped lines are where we have a specific phase. So, solid requires the least energy, liquid intermediate, and gas most. In the middle, we have melting as we add energy and vaporization as we add energy from liquid to make gas. However, you do need to remember your heat calculations, your heat equations, because I might ask you to find the heat needed to change ice at negative 10 degrees Celsius to a gas at 110 degrees Celsius. So you would need to calculate the heat required to increase the temperature, or use the specific heat capacity formula for all of these sloped lines. And then when you're undergoing melting or vaporization, you will need to use the heat of fusion and heat of vaporization equations. So to calculate heat energy changes, when the phase is changing, use Q equals mH sub F or Q equals mH sub V. When the temperature is changing, we use Q equals mc delta T, and you can add the results of two or more equations together to determine heat energy change over a longer period. Cooling curves are just like heating curves, except you're going the opposite direction. So you are decreasing the energy, and it is exothermic, not endothermic.